Hello, we're going to look at relative atomic mass and what that means, and hopefully we're going to learn how to calculate relative atomic mass when we have different isotopes that have different masses. So what do we mean by relative atomic mass? Well, relative means you're comparing it to something. So we're comparing all atomic masses to the isotope carbon-12. The mass of carbon-12 isotope is defined as exactly 12 atomic mass units. So if we had one atomic mass unit, that would be 1/12 of a carbon-12 mass. The lightest atom we have is hydrogen. It's 1/12 of the mass of carbon, so it has a relative atomic mass of 1. So as you can see here, we've got 12 hydrogen atoms to one carbon-12 atom. So therefore it has a relative atomic mass of 1/12 of carbon, and that's 1 atomic mass unit. Magnesium is twice as heavy as carbon. As you can see here, we need 2 carbon-12 atoms to actually make up 1 magnesium. So because it's twice as large, it's got to be twice as large as 12, so therefore it's 24 atomic mass units. Now if you look at a periodic table, something like this, you can see that the top numbers, which is the relative atomic mass, they're not all whole numbers. Now I wonder why that is. The answer is isotopes. Many elements have different isotopes, and just to remember what an isotope is, we say an isotope is elements that have the same protons but a different number of neutrons, or it's with the same atomic number, that's the bottom number, but a different mass number, that's the top number. So here's an example. We've got isotopes of helium. We have the isotope that has the top number, the relative atomic mass of 3, and we have the isotope with the relative atomic mass of 4. But as you can see, above it is what we call the abundance. That means how much you have in a certain sample of helium. So for helium-4, we have 99.99% of all the particles will be helium-4, whereas the helium-3, it's only 0.01% of all the atoms will be helium-3. So if there are two different masses compared to carbon-12, what we're going to need to do is find a way to calculate a mean mass. Now up to now, when we're calculating a mean, what we would do is take the numbers and divide it by 2. So there's 2 isotopes, so we'll add 3 and 4 together and divide by 2. But that is not what we're going to do. And the reason for that is because if you look at the abundance, 99.99% of all of the atoms are helium. So it's not fair to just assume that it's 50%. Just to put it in context, 99.99% means that only 1 in every sample of 10,000 would be helium-3, and the other 9,999 would be helium-4. So it's more likely that the relative atomic mass is going to be much nearer 4 than it would be 3. So here's how we are going to do it. We're going to take into account the abundance, multiply it by the mass, divide it by 100 because it's percent, and then we get our answer. And then we're going to put it to 1 decimal figure. So this means that the relative atomic mass shown in the periodic table is not only just a comparison with carbon-12, but it's also a mean of all of the isotopes of any element, taking into account how much you've got of each isotope. So let's look at chlorine. How do we calculate relative atomic mass? Well, in chlorine, 75% of chlorine exists as chlorine 35. That means it has a mass of 35. And 25% has a mass of 37. So if you look at it as a pie chart, you can see that a quarter of all the atoms in any sample will be chlorine 37, and 3/4 will be chlorine 35. So 3 times as many will be chlorine 35 as chlorine 37. So the atomic mass is an average of the masses of both the isotopes taking into account their relative proportions. So here's how we're going to calculate it. And in these steps, we're going to follow these steps every time we calculate a relative atomic mass. So we're going to multiply the mass numbers by their abundance. So 35 times 75. Put that in brackets to keep it nice and tidy, keep it all in its own little pockets. Plus 25 times 37, again in brackets. We need to divide it by 100 because those numbers are percent. So that's like 75 out of 100. And then we can calculate it on our calculator. So that's 35.5. Now we would at this stage round it to 1 decimal figure, but it's already rounded to 1 decimal figure. So the relative atomic mass of chlorine, taking into account the different isotopes, is 35.5. Right, let's have a look at another example. We're going to look at carbon. So carbon has 3 isotopes. Carbon-12, which has 98.9% of all of the atoms. Carbon-13, which accounts for 1.1% of all the atoms. And carbon-14, which accounts for less than 0.1% of all the atoms. So here's our way of doing it. Okay, so we're going to multiply 12 by 98.9, put it in brackets, add it to 13 times 1.1, plus 14 times 0.1. Divide it by 100 because it's percent. Calculate it, so that's the answer that the calculator will give you. And because the periodic table needs it in 1 decimal place, we are going to round that to 12.0, which is what we expected. Remember, we said that carbon has a relative atomic mass that is nearly exactly 12. Okay, it's your turn. Copper has 2 naturally occurring isotopes. 69% of all copper is copper-63. 31% of all copper is copper-65. What is the relative atomic mass of copper? So here's your instructions. I want you to now go and try and do your calculation. Pause the video and then come back when you finish your calculation. Okay, so we've got 63 times 69 plus 65 times 31, divide it by 100, 63.62, and step 3 to 1 decimal place, 63.6. Now I hope that you all got that answer. Okay, second time. Boron has 2 naturally occurring isotopes. 20% of all boron is boron-10. 80% of all boron is boron-11. What is the relative atomic mass of boron? So here's your instructions. Again, I want you to pause your video and do the calculation and then come back when you want to check your answer. Okay, we've got 10 times 20 plus 11 times 80 divided by 100 gives us 10.8. And that's already rounded to 1 decimal place, so the answer is 10.8. I hope you were successful. Okay, third example. Thallium has 2 naturally occurring isotopes. 30% of all thallium is thallium-203. 70% of all thallium is thallium-205. What is the relative atomic mass of thallium? There's your instructions. I want you to pause the video and try and do your calculation. Okay, we've got 203 times 30 plus 205 times 70 divided by 100 gives us 204.4. That's already rounded to 1 decimal place, so that is our answer. Okay, fourth example. Right, potassium has 2 naturally occurring isotopes. 93.2% of all potassium is potassium-39. 6.8% of all potassium is potassium-40. What is the relative atomic mass of potassium? Here we have our instructions. Pause the video and attempt the calculation. Okay, we've got 39 times 93.2 plus 40 times 6.8 divided by 100 equals 39.136. We need to round that to 1 decimal place, so that is 39.1. Okay, this one is slightly more difficult because it involves 3 isotopes. So magnesium has 3 naturally occurring isotopes. 79% of all magnesium is magnesium-24. 11% of all magnesium is magnesium-25. 10% of all magnesium is magnesium-26. What is the relative atomic mass of magnesium? So here's your instructions. Pause the video and have a go at this one. Okay, we've got 24 times 79 plus 25 times 11 plus 26 times 10 divided by 100 gives us 24.31. Round it to 1 decimal place and we get 24.3. Okay, last example. Silicon has 3 naturally occurring isotopes. 92.2% of all silicon is silicon-28. 4.68 of all silicon is silicon-29. 3.08% of all silicon is silicon-30. What is the relative atomic mass of silicon? Now you can either pause the video now and try and do it without your instructions, or here's the instructions and you can try from now. Okay, so we've got 28 times 92.2 plus 29 times 4.68 plus 30 times 3.08 divided by 100 gives us 28.0972. Rounded to 1 decimal place, 28.1. I hope this video helped and you're now able to calculate relative atomic masses.